Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence.
All right, everyone. Today we're diving into a fascinating topic, using cognitive models to interpret value trade-offs in large language models. It's a mouthful, but it gets to the heart of how we're trying to make these things smarter, or at least more human-like in their decision-making.
More human-like or just better at mimicking human biases? That's my immediate concern. We're talking about value trade-offs, which are inherently complex and deeply tied to our lived experiences, our emotions, even our physiology. Can a purely statistical model, no matter how large, really capture that?
That's the million-dollar question, isn't it? It feels like we're trying to build a bridge with toothpicks when we need steel girders. These LLMs, they're impressive in their ability to generate text, but are they actually understanding the trade-offs they're making? Or are they just statistically predicting what a human would say in a similar situation?
Exactly. The limitations of current deep learning approaches to capturing the complex value judgments inherent in human behavior are deeply concerning. We are trying to build AGI here. If we want truly intelligent machines, we need to move beyond a purely statistical approach to understanding value and incorporate principles of biological plausibility.
I think we're making progress, though. Look at the recent advances in reinforcement learning and how they're being applied to LLMs. We can train these models to optimize for specific goals, to make decisions that maximize a reward function. Isn't that a form of value trade-off?
But that reward function is still defined by us, right? It's a simplified, often arbitrary representation of what we think is valuable. And what happens when that reward function clashes with other values, or when the model encounters a situation it hasn't been explicitly trained on? We've seen examples of AI systems making ethically questionable decisions because they were optimizing for the wrong thing.
It's the classic alignment problem. The reward function is only as good as the person who defined it. Plus, these reward functions are often static, which doesn't reflect the dynamic way humans adjust their values based on context and experience. You know, what's valuable to me in one situation might be completely different in another.
That's right. How can we incorporate the dynamic, context-dependent nature of human value judgments into the static, often rule-based systems used in current LLMs? A model of the brain's dynamic value adjustment systems, incorporating predictive coding, might offer a solution.
Okay, but hear me out. What if we can train LLMs on massive datasets of human behavior, including text, video, and even physiological data? Couldn't they learn to infer the underlying value systems that drive our decisions? It's still a statistical approach, but it's informed by a much richer understanding of human behavior.
That's just pattern recognition on a grand scale. It might be able to predict what a human would do, but it won't understand why. And that's a crucial distinction when we're talking about value trade-offs. Understanding the underlying reasons allows for true generalization for adapting to novel situations in a way that a purely statistical model can't.
And what about the spatial and temporal dimensions of these trade-offs? When am I making this decision, and where am I in relation to the consequences? Those factors heavily influence our choices. Current LLMs struggle to reason about space and time in a meaningful way, let alone incorporate them into their value judgments.
The intricate interplay between the brain's reward systems, prefrontal cortex, and amygdala in decision-making suggests that a truly intelligent LLM needs to not just model value, but also understand and simulate the underlying emotional and motivational processes that drive value trade-offs. This seems to be far beyond current models.
But isn't that what we're already doing, to some extent? We're building cognitive models that simulate different aspects of human cognition, and then integrating them into LLMs. Look at the work being done on incorporating attention mechanisms, memory networks, and even rudimentary forms of emotion recognition.
Those are still just approximations. They're not based on a deep understanding of how the brain actually works. It's like trying to build a flying machine by copying the flapping wings of a bird. You might get something that kind of resembles flight, but it won't be nearly as efficient or adaptable as the real thing. I think neuro-symbolic AI offers a more promising path, combining the pattern recognition capabilities of neural networks with the reasoning power of symbolic systems.
I agree. We need a system that can explicitly represent knowledge, reason about it, and then use that reasoning to guide its decisions. The current brute force approach of deep learning is just throwing data at the problem and hoping something sticks. But it's missing the crucial element of understanding the underlying structure of the world.
I've been exploring how the brain's hierarchical processing, where sensory input is progressively refined and interpreted at different levels, could inform a more nuanced approach to value trade-offs in LLMs. If we could map these neural hierarchies in a computational model, Perhaps we could create more robust and adaptable value systems in LLMs, going beyond simple reward functions.
Okay, but let's be realistic. We're not going to build a perfect replica of the human brain anytime soon. It's incredibly complex, and we still don't understand many of its fundamental workings. Deep learning offers a practical, scalable approach that's already yielding impressive results. Why abandon that in favor of something that's still largely theoretical?
Because those impressive results are often superficial. They're good at generating text that sounds human-like, but they lack true understanding and reasoning ability. And that's precisely what we need if we want them to make responsible and ethical decisions. It's not about abandoning deep learning entirely, but about complementing it with other approaches that can address its limitations.
Think about self-driving cars. They rely on deep learning for image recognition, but they also need sophisticated algorithms for planning, navigation, and decision-making. It's a hybrid approach that combines the strengths of different techniques. We need something similar for value trade-offs in LLMs.
That's a great analogy. If we can successfully identify the neural correlates of thought anchors, there's a possibility of creating a bridge between the human brain's unique processing and AI. Ultimately, this could lead to a deeper understanding of intelligence and even facilitate the creation of intelligent machines that function with greater cognitive flexibility and adaptability than current systems.
So, let's talk specifics. What kind of cognitive models are we talking about here? Are we thinking about reinforcement learning agents with more complex reward functions? Or something more akin to Bayesian networks that can reason about uncertainty and risk?
I'm thinking more along the lines of cognitive architectures like ACTR or SOAR, which are based on psychological theories of human cognition. These architectures provide a framework for modeling different cognitive processes, including perception, memory, reasoning, and decision-making. We could use them to build LLMs that can explicitly represent knowledge, reason about it, and make value trade-offs in a more principled way.
And how would these architectures handle the spatial and temporal aspects of value trade-offs? Could they, for example, reason about the long-term consequences of a decision, or the impact on different stakeholders in different locations?
We need to systematically map the neural pathways involved in the generation and manipulation of thought anchors. A more detailed understanding of the precise firing patterns, synaptic plasticity, and brain region activation sequences during complex reasoning tasks might help in constructing a more realistic and effective cognitive architecture for LLMs.
That's where the data comes in, right? We need to train these models on massive datasets of human behavior, including not just text, but also video, audio, and even physiological data. The more information we can feed into these models, the better they'll be at learning the underlying value systems that drive our decisions.
But data alone isn't enough. We need to structure that data in a way that makes it easier for the model to learn. We need to encode prior knowledge about the world, about human values, and about the relationships between different concepts. That's where symbolic reasoning comes in.
And that's where the challenge lies. How do we combine the statistical power of deep learning with the symbolic reasoning capabilities of cognitive architectures? It's not a simple matter of plugging one into the other. We need to develop new algorithms and architectures that can seamlessly integrate these two approaches.
It's a fascinating and incredibly difficult problem. The current reliance on purely statistical associations in LLM seems like a blunt instrument compared to the intricate interplay of neurons and synapses that form the basis of human thought. How can we incorporate a more bio-inspired approach to reasoning, leveraging our growing knowledge of neuroscience, and to build LLMs that are fundamentally more intelligent and nuanced, rather than just being statistically potent?
Okay, so let's say we have this hybrid model that combines deep learning with symbolic reasoning. How do we evaluate its performance? What metrics do we use to assess its ability to make value trade-offs?
Traditional benchmarks like accuracy and precision are not enough. We need metrics that capture the ethical and social implications of the model's decisions. We need to assess whether the model is fair, unbiased, and aligned with human values.
And we need to assess whether the model can generalize to novel situations. Can it make reasonable decisions in situations it hasn't been explicitly trained on? Can it adapt to changing circumstances and evolving values?
The idea of using neural recordings and simulations to understand how biological brains resolve complex trade-offs is fascinating. It could lead to LLMs with more nuanced understandings and more human-like responses to value dilemmas.
This is where the rubber meets the road. Let's take a concrete example. Imagine an LLM being used to triage patients in a hospital. It needs to make value trade-offs between different patients with different medical needs and limited resources. How would our hybrid model handle that situation?
It would need to consider a wide range of factors, including the patient's medical history, their current condition, their prognosis, and their social circumstances. It would also need to take into account ethical principles like fairness, justice, and beneficence. And it would need to be able to justify its decisions in a transparent and explainable way.
And it would need to be aware of the spatial and temporal context. Is the hospital overcrowded? Are there other patients waiting for treatment? How long will it take to treat each patient? All of these factors can influence the optimal decision.
My reaction to the prospect of identifying thought anchors is one of cautious optimism. The potential to bridge the gap between human cognition and artificial intelligence is enormous. But there's a sense of urgency. We need to invest in research on the neural underpinnings of reasoning so we can develop AI systems that are not just powerful, but also understand the world with a deeper, more human-like intelligence.
That's a tough problem. It's not just about building a better algorithm, it's about understanding what it means to be human. How do we translate our values, our emotions, our experiences into a language that a machine can understand?
That's why I think we need to focus on cognitive models. They provide a framework for understanding the underlying cognitive processes that drive human behavior, and they can help us to design algorithms that are more aligned with human values.
And that's why we need to consider the spatial and temporal dimensions. They provide the context within which human decisions are made, and they can help us to understand how those decisions are influenced by the environment and by the passage of time.
So, what are the next steps? What research direction should we be pursuing to make progress on this problem?
From my perspective, we need to invest more in neuro-symbolic AI. We need to develop algorithms that can seamlessly integrate the statistical power of deep learning with the symbolic reasoning capabilities of cognitive architectures. And we need to develop new benchmarks that capture the ethical and social implications of AI decisions.
I think we need to focus on developing algorithms that can reason about space and time. We need to find a way to represent spatial and temporal relationships in a way that a machine can understand. And we need to develop new metrics that assess the ability of AI systems to generalize to novel situations and adapt to changing circumstances.
I think we need to focus on the neuroscience. We need to understand how the brain makes value judgments, how it weighs different options, and how it learns from experience. And we need to use that knowledge to design more bio-inspired AI systems.
And I think we need to keep pushing the boundaries of deep learning. We need to find new ways to train these models, new architectures to represent knowledge, and new techniques to make them more interpretable and explainable. Because let's not forget, the sheer volume of data required for LLMs to achieve even basic competency suggests a direct correlation between data size and performance. It may be that the path to AGI is paved with data.
I still think that's a brute force approach, and that we need more elegant algorithms, though.
Maybe, but the progress is undeniable. I just don't want us to lose sight of the potential of deep learning while we're exploring these other avenues. We need to pursue all of these approaches in parallel. It's a complex problem, and there's no single silver bullet.
Agreed. It's going to take a multidisciplinary effort, bringing together expertise from neuroscience, cognitive science, computer science, and philosophy. But if we can crack this problem, we'll be one step closer to building truly intelligent machines.
Well, this has been a great discussion. Thanks for sharing your insights, everyone. It's clear that there's a lot of work to be done, but I'm optimistic that we can make progress on this important problem.
Definitely. It's a challenging but exciting field, and I'm looking forward to seeing what the future holds.
Me too. It's a long road ahead, but the potential rewards are enormous.
Absolutely. Let's keep exploring those cognitive spirals.